In his book Outliers, author Malcolm Gladwell argues that more baseball players have birth dates in the months immediately following July 31st because that was the age cutoff date for non-school baseball leagues. Here's a sample of frequency counts of months of birth dates of American-born MLB players starting on January. So, 387, that's how many in January, 329, that's how many in February, and so on. Using a .05 significance level, is there sufficient evidence to warrant rejection of the claim that American-born Major League Baseball players are born in different months with the same frequency? So clearly we're doing a hypothesis test because it says test the claim. Let's change the color because let's do that one because it's fun. What is that, black? No, dark gray. That's gray? Wow. Okay. Um, I gotta go click on that. All right. So, um, so we'll have null hypothesis, alternative hypothesis, and as always, the null hypothesis that includes equality. And so for this one, when you're comparing like a frequency distribution, which is essentially what this here is. I mean, you could say month and frequency, and then say January, February, March, etc. And for January, it would be 387. February would be 329. March would be 366, and so on. Okay, so when you have a frequency distribution, um, then and you're saying, hey, I want to compare in this frequency distribution what what we actually saw, what we observed versus what we expected. Okay, and the null hypothesis is going to be the observed values are are equal to the expected values or close enough. Okay. So the H1, the alternative hypothesis, is just going to be not all of them are equal. Okay. All righty. So what do we do? Well, glad you asked. We are going to plug in the observed values, the 387, 329, and all that, into the stat guy here. And let me pause this. Okay, so all of the observed values are in L1. That's where you want to have them. That's just the way the formula works that we're going to be using, or the program, I should say. Okay, then in L2, we want to have our expected values because we need to compare the observed with the expected. Uh-huh. Well, they don't tell us the expected, but they do, we do say, well, we expect that, what we would actually expect is that each month has about the same number of people from Major League Baseball born in that month. So I got a great idea. Let's go to stat over to calc and let's do the stats for L1. And if you add them all up, it's 4515. Okay. So 4515 people were in the sample. And, there's some of them were in January, some were in February. So if we take that 4515 and chop that up, over 12 months, then we would expect 376 and a quarter. I know you can't have a quarter for birth, but that's okay. The formula still works. 376 and a quarter people born in each month. That's what we would expect. So I'm going to go. So what I want to do is go stat over, and then I need to put 376 and a quarter in there for each of the 12 months. I need 12 of those. Okay. So let me pause again here. Okay, so I have all of the observed over here on the left, expected on the right. So now we can go to stat over, and we want to use the chi-squared GOF test, goodness of fit. Okay, so in other words, how well do the observed values and the expected values fit each other? Okay, is there a significant discrepancy between them, or do they fit, close enough? So we'll do that. So the observed values are in L1, the expecteds are in L2, and then DF stands for degrees of freedom, and that is just it's usually it's one minus the sample, or it's the sample size minus one. But in this case, that's not really going to make sense. So we're going to do the number of categories minus one. Okay. Or in other words, you can just say 11. Either way is fine. And then we'll go down to calculate. And the p-value is quite small. Again, that happens frequently, but certainly not always. So we've got the p-value is 4 times 10 to the negative 15. So that's 0.00000, 14 zeros, and then our 4. Which obviously is less than alpha, whatever that is, 0.05. So we would say there is sufficient evidence to reject the claim that the observed and the expected match up. Therefore, it appears that the how many people are born each month is not the same. I mean, obviously, it wasn't the same in our sample. Okay, but based on the sample and this test, it is sufficient. Those numbers are sufficiently different that we're going to go with H1. Okay. Um, and then the follow-up question was, do the sample values appear to support Gladwell's claim? Well, the sample data appeared to support his claim because he said, hey, it's not the same for every month. Okay. However, again, this is looking at every month of the year. It's not focusing in on where is it? On the months following July 31st or immediately following. Okay. It just says so this test appears to support Gladwell's claim, but it does not verify it. Okay, it says, well, there seems to be some differences, but who knows? Maybe more, if you look at the data more closely, maybe more of them are not following July 31st, but coming before it, or a little bit right before and a little bit right after. And so this doesn't guarantee his claim is correct. It just says, hey, there appears to be, a reason to pursue his claim further. Not every month has the same amount. So that's kind of, what's going on there. Okay, in a study of high school students at least 16 years of age, researchers obtained survey results summarized in the table below. Use a 0.05 significance level to test the claim of independence between texting while driving and irregular seatbelt use. So I think that's mainly going to be the seatbelt wasn't on, but it could just be, well, I put the shoulder strap behind me or, whatever. But I think it's mainly, I think, his seatbelt was not engaged. Are those two risky behaviors independent of each other? Okay, so in this problem, a couple of things tip us off of what we're going to do. One is we have what's called a contingency table, okay, where you have one variable listed here, another variable listed here, and then all the people that fall into each of those categories. Okay, so yeah, these are the people. We didn't have our seatbelts on, and we were texting while driving. Okay, so that's that's definitely the people who are more likely to have problems. And then here's the really good ones. We were not texting while driving, and I had my seatbelt on. Okay, anyway, so that's kind of what's going on. So when you see a contingency table, typically you're going to do what we're about to do. Another thing that tips you off is that it says test the claim of independence between texting while driving and irregular seatbelt use. So when we are doing a test of independence, then that's the main thing that tips you off. So texting while driving and irregular seatbelt use. Those are the two variables. Okay. So when you have a test of independence, the null hypothesis is is always the same thing. The variables are independent. Okay, and H1 is the variables are dependent. So there's some type of a relationship. If one of them happens, it affects the probability of the other one happening. If, for dependence. Okay. But independent basically means, oh, well, if one of them happens, that doesn't affect whether or not the other one happens. That's independence. Okay. So there's a couple of ways we can do this. We can use the list again, stat enter, which I'm not going to do. Instead, I'm going to show you something just a little bit different. Okay. And we're going to shrink that down just a wee bit there. Okay. And why doesn't that move over? Oh, well, whatever. Okay. Um, so what we're going to do is we're going to go into the matrix. Notice it says matrix right here in blue. So we'll go blue matrix. And we'll go over to edit. And we want to, there's matrix A, matrix B, matrix C, kind of like in the y equals menu, there's y1, y2, and so on. We want to do matrix A because that's the way the program we're going to use is set up. It always refers to matrix A every time. So you really have to do it this way, and that's okay. It certainly doesn't make it any tougher. Okay. Now we need to put in all of this data, okay? There are 2 rows and 2 columns. So we need a 2 by 2 matrix. Okay. So you just put them in the way they appear in your table. Okay. So we've got the matrix. Okay, we're going to quit out of there, and then we're going to go to stat, over to test, and up to chi-squared test. So this is what we're going to use for test of independence. Okay, so our observed values, okay, yeah, they're in matrix A, but our expected values, well, we never did create matrix B. Well, here's the great thing. This program creates matrix B for you, okay? You never even have to look at it, although you can. So, yeah, matrix B, cool. All right. So I'm going to go down to calculate. And we got a p-value as, what a surprise, it's small. Okay, but like we've seen, sometimes the p-value is large. So the p-value is 0.1234 zeros, and then like a 1.5, which is clearly less than 0.05, the alpha, the level of significance. Okay, therefore, it looks like we have sufficient evidence to reject the claim of independence. Okay, so it would appear that based on what we're seeing here, that whether or not a teenager, or well, I'm sorry, a high school student who's 16 years or older, but still a high school student, so for those people, whether or not they decide to text while driving and whether or not they have irregular seatbelt use, it seems that those 2 behaviors are dependent. Okay. In other words, the more likely you are to do one of those things, the more likely or less likely you are to do the other. So there is some type of relationship. Now, it might be, this doesn't tell us that, all right, if you text while driving, you're more likely to not wear your seatbelt. Or if you do wear your seatbelt, you're more likely to not text while driving. It doesn't say that. But what it does say is that uh, there's some type of dependence there. Okay, maybe, who knows? It's not likely, but um, maybe if you don't wear your seatbelt, then uh, that affects that affects your texting while driving. Maybe not wearing a seatbelt affects you in the way of you do or you do not text while driving. So who knows? We don't know. We haven't explored that. We just know that the 2 variables appear to be dependent. Oh, and then one other thing we can do is, you certainly don't have to, but you can go back into the matrix, and then we can take a look at, we can go to edit, matrix B, and see what they chose for us. Okay. And there's a formula for doing all this if you want to do it by hand, but these are the observed val or the expected values down here that the calculator just pumps out for us. So, that's really nice.